Hello, everyone. Well, first to Hamai. Most people know me today as a GStreamer developer, longtime contributor. I support people on Discourse these days. But in reality, a good part of my time is spent developing the Linux kernel, developing new codec API, and improving the codec support, helping with the codec maintenance in the Linux kernel because they kind of struggle to get things merged. But overall, that 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 actually explains my big focus on Linux support within GStreamer and my interest in zero copy, DMBUF, OpenGL, and hopefully Vulkan in the future. One thing about me is that I'm a month away from being 15 years old at Collabra as a consultant, and I thought I would use actually that little aging flavor for this. So I would talk a bit about my work, my journey as an embedded open source developer, and what it means, what we do, and that's going to walk you through how we solve OpenGL zero copy issues for different customers. Of course, everything starts with a challenge, not necessarily for us, but for our customers. And these challenges comes with various parameters. Sometimes you got a brand new hardware from 2030. Well, not the case here. It was a customer with farming equipment on existing product running IMX6. Fortunately, the Quad Plus version, which is a little faster, but still, it was designed in 2011 for the context. So 1280 by 800 touchscreen display, that was our parameters. But interestingly, they were running latest version of Qt 6, mainline Linux, and mainline GStreamer, actually the latest stable release. The goal of that project was to use the existing software and be able to remote render it at another location. Consider that in farming these days, with you can have machines that are about 80 meter long. You might need to view things remotely. That could be a use case. You could have technical support, remote technical support, and stuff like this. And basically, the idea is that they would take the Qt 6 application, encode it in H.264, put that into RDP, and remote view it with a standard RDP viewer. And yeah, for that, they had a very simple basic plan. So they use EGLFS, they don't use a compositor. So they thought of using QML6 GL source as a capture element, the V4L2 encoders, which is all mainline. I mean, they were thinking that, hey, that board has been around for a while, the mainline support we're trying to pay off all the work we did mainline on this board, so why not? And then AppSync, and then they would take care of the RDP playback. Well, this is not a transcript. This is just me making it up. But basically, their statement was, well, we have something kind of working. We had to skip the GL thing and go back as soon as possible to CPU, color convert on CPU, encode in software. But at least it kind of worked, but it's way too slow. We won't figure out ourselves. We need help. And that's how it started. When we get that, of course, we start with a plan, and we have rationals for these plans. And I'll walk you through the rationals, and also I'll bring up some of the work that my colleague Jacob has been doing that I wanted to reintegrate into this project so we could kind of gain from other active projects in the field. So the plan was to, just like anything you do embedded, the more driver, the more Linux development you'll have to do to fix the bugs or adjust, and that's a huge amount of time, especially for small teams. So I've told myself, I'm going to try, I know the GPU is slow, but I'm going to try to use only the GPU and the encoder. So I went into like the QML6 source examples, and that was basically the recommended pipeline. So QML renders upside down, you need a flipper to put it back up. So there's your GL flip. Color converter, because the encoder uses NV12. We do GL in RGBA only in GStreamer. Finally, the download element. I'll tell a bit more about that. And V4L2 encoder. Now I knew that I mean, I wrote it, so I knew that V4L2 encoder was handling DMA buffs at his input, and it was able to offer these DMA buff as a pool. And the new thing that is coming, that is under work by Jacob, is that the GL download is able to query for that pool of DMA buff, which is the low-level memory handle on Linux, and wrap them up so they're usable by upstream GL. So instead of being a downloader, it's actually an adapter where it envelopes everything, and I'll tell you more about that soon, in order for the upstream element, in this case GL converter, to write to. It's not like the most efficient pipeline. It's well known that there's memory transfer at many places here, but it was expected to be fine as soon as it was a zero copy. Now, let me tell you a little bit more about OpenGL Linux support. So most of the Linux extension in OpenGL are in the EGL library, which is kind of a more native library. It's not context-oriented anymore. It's really about wrapping resources. And, well, a DMA buff is just a file descriptor. You can query its size, and that's it. It doesn't say it's an image. It doesn't have to be an image. So you need to tell EGL, well, this is an image, and an image has a width, a stride, a format, and many other parameters. And typically in GStreamer, we've implemented a while ago this support where we would put that DMA buff into an EGL image, and then we would use it to render for playback purpose. But GStreamer have always supported to render from GL textures, but also into GL textures. And that's what we're changing now. We're going to start using the EGL image to render into it. So the texture will no longer have a dynamically allocated backend. It will have a storage that we've chosen, decided, with a format that we've chosen, which means I can control that this format is going to be compatible with my encoder. Why didn't we do that before? Well, until this extension made by my colleagues, Daniel and Pekka in Kronos, GL's specification, it was impossible because in order to do that, you need to know a bit more about what kind of format your GL stack support. Otherwise, you're in trial and error, and at runtime, when you get errors, it's really hard to recover from it. So with the import modifier extension, we can now enumerate formats, and on top of it, there's a little extra, this little boolean that not everybody knows about, external only, which basically tells you if you can render from the texture or if you can also render to the texture. So if it's an external only format, it's only a format you can read from. And you have to use it with a special sampler. Notably, you don't have access to all the filtering, all the cool stuff. So something to watch for when you do this reverse EGL image usage in GStreamer, you can only use the formats that are not external only, which is usually very limited. But most of the time, you have at least one RGBA linear format, which is going to be perfect for all the situations. The implementation from Jacobs uses the new DMA-DRM negotiation support because it makes everybody's life easier. As soon as you've negotiated the caps with these, if you get a pool, you know that this pool will contain DMA buff. While back in the days, we had to actually allocate a buffer and look at that buffer to see if it's actually a DMA buff, and then free it because you don't need it. So well, we had a plan. Just like any of these projects, there's high level of risk. If some of you are developers and I've been into that, you know that it's not always going to work right away. So the exercise is always to, as quickly as possible, identify all the biggest issue and the troubles ahead of time. There's a one-time cost every project have, and you have to pay for that. You need to set up. So we're speaking about farming equipment. It doesn't fit my backyard. So there was no way I would work on the customer device. But this is devices like I've been working on for 10 years. We have stocks of it. Well, that's an interesting one because when we started the projects, We were two developers. We started shipping those boards around, and actually, one of my colleagues figured out that he was looking at a schematic, and he was like, "There's chips missing on my board." Turns out that those development board with age, the solder can crack and the pieces can fall off. So it's been an interesting challenge to get the project started because of these kind of issues. But anyway, I've picked the latest Yocto because my customer was using Yocto. We would deliver any changes we do as patches because it was much faster for them to integrate. I've put that into our Collabora GitLab CIs so that I can save my machine and I can keep my office cool. And configure the Linux kernel, prepare the GStreamer patches we already knew about, notably Jacob's patches to be included. So yeah, there was nowhere wrong. And then the testing started. So we needed a test application. That's really nice. There was one in QML6 source examples. So I picked that test, I modified it to make it a streamer. I've changed a couple of things. It was flipping from two texts. I've changed it into a counter. I added ability to click so something would change and you would see the reaction time. So engineering level UI, and you'll see it later. I have a live demo at the end of this. Then from there, yeah. So from there, I needed to test if actually with that GPU, this old Etnaviv with GLES 2.0, I was able to use at all Jacob patches. And fortunately, he had a very simple, straightforward test with GL test source, download, KMS sync. He had patched KMS sync to make it work. And yeah, that worked. So that was really, really good news for the project because if that did not work, maybe we would have had to cancel the project. So yeah, there we go. And then we also had the idea that it should work without zero copy because there's work to be done on the V4L2 element to get the DMA, DRM negotiation and everything. And yeah, it should work. Unfortunately, it was not such an easy ride. So first thing we discover is that, well, QML GL6 source is a bit of a candy implementation, a quick translation from the Qt 5 version. And it needed a little love. So it was leaking. So after a couple of seconds, it would stop. And it was especially fast on that board with like less RAM and using also CMA, so contiguous memory for the GPU. So it kind of scatters itself. It breaks itself after a while. There was a lot of delays. That's something we didn't figure out immediately. It took a bit of time, but we had workaround to keep producing frames, so it was not as visible. So we kind of delayed that. And it only worked on Wayland. And my customer is not using a compositor. They're using EGLFS. And that's another one we had to think about and do some research to figure out. So yeah, eventually and then there was a bunch of negotiation error. And I was aware of these because I was getting feedback from the Raspberry Pi people. They had a big struggle with the encoders. So it wouldn't negotiate if there was no frame rate, which a UI doesn't have. It produces a frame if you click. If you don't touch it, nothing's happening. It didn't negotiate if the colorimetry wasn't right. There was a bunch of little things that needed to adjust. But the biggest issue was that GL convert just failed trying to do NV12. And turns out that back in the days in GLES 2.0, it was actually optional to be able to run a shader and write into multiple textures. And if you know a little bit about pixel format, NV12 is two textures. You got the chroma and the luma, other way around. But you got the luma and the chroma separate. And the way we do that in GL is that we say, hey, here's a R8 buffer, here's a RG88 buffer. And then you have one shader that renders to both. So yeah, we needed a replacement for GL convert. We also noticed that the memory was maxed out, especially on my development board, which is not the Quad Plus, but it's only the Quad. And that causes the DSI to flash blacken with black frames. But it's a hardware issue, so we just assume that because they fixed it on the Quad Plus, it would work. And if I reduce the bandwidth. Now, speaking of bandwidth, it's always good to have the knowledge to analyze your bandwidth utilization. In the presentation from AMD, from Harris, he said that it's the memory transfers that consume your bandwidth. So it's not about copies, it's about transfer. So you're taking pixels and you're making other pixels and you're writing it back to memory. That's what consumes your bandwidth. If we look at the design of QMLGL6 source, uh, the principle is that it let GL render, it's let Qt render its stuff, and then it steals the back buffer. So it literally copies a texture into another texture. So that's one pass. GL video flip actually takes the image and flip it over. That's another pass. If we were to be able to use GL convert, that would be another pass, but it did not work. Then in software, GL download takes those pixels from the GPU memory and put that in a virtually allocated memory. That's another copy. And to another format. And then in order to encode it in hardware, you need to put it back into memory that is valid for the encoder, another copy, and here goes your bandwidth. And that's pretty much done on such a little device. Okay, I mean, I have a lot of experience with IMX6. I knew exactly what was the alternative to this converter. It was already mentioned initially that we could use actually a chip called IPU-V3. So IMX6 is a bit fancy. So it has the IPU-V3, which does the interlacing, scaling, color conversion, rotation, flippings, and everything. And this is a block that can support at the input both a memory, like reading from the bus, or a signal. And at the output, it can also do memory or signal. And then programmatically, you have multiple instances of these. You can plug them into your camera to be fed directly from the camera as a signal, and then out to memory. You can plug it into your display controller, in as memory, and then out straight to your display. And you can use it in a memory to memory fashion where you just got memory in and memory out, and that's what we're going to use. Support for that was already developed before L2 convert. We could get rid of GL the filter that flips the image because you can flip and convert at the same time. The only downside is it's a staging driver. And if you're doing embedded development and you're going to pick a staging driver, make sure you got a kernel developer around. In this case, it was myself, but because there's going to be work. There's going to be work. There's a reason why this driver is staging. It means that there's still some to-dos. And here comes the plan B. Actually, I was happy with the plan B because it's a much simpler pipeline. So we got QML6 source, GL download, V4L2 convert, and then V4L2 H.264 ANC. That's it. There's a copy of the back buffer in GL6 source, and then it's 0 copy all the way to the converter, and then it's 0 copy to the encoder, and that's it. And here comes the second prototyping stage, because we changed the plan. We could go in implementation right away, but you never know. You have to check what's going on. You have to plan. You have to know how much it's going to cost, mostly. What we found next, well, because we skipped all the GL elements, and I only tested with converters and stuff like this, I didn't think that GL6 source would be missing the allocation query. So it was actually not using any of the downstream pools. It was just allocating dynamically textures, which would explain the fragmentation problem also that we had, because it was not using things from a pool, was not being reused. So here we go. We had to implement that. The IPU v3 did not support RGBA. I mentioned earlier, our GL stack does only RGBA. So that was kind of a problem. Fortunately, I had the spec, the hardware spec. It was supported in the spec. It was just not implemented in the driver. So problem was straightforward to fix. We also had a weird color where we ended up with full range stuff being rendered as if it was limited range, which scales up the color and create kind of saturation all over the place with blobs and spots. If you have a gradient or anything, it's quite a mess. So, and yeah, I figured out that the driver has been upstreamed into staging before there was an API in V4L to actually support changing the color space, so to be implemented. Oh, but overall performance, that's the good news. Just that was already better. Like, it was already kind of acceptable. at best, I would say. And then goes the implementation. And for that, we had to fix the leak I mentioned. So that's the merge request number for the leak. I noticed a crash if you if you don't set use default FBO. I fixed it. The feature is still broken. It's a design error in the QML6 source. We have ideas how to fix that, just more work. We finally found that when you're actually using EGLFS, the GL configuration does not have alpha, which has a consequence on the format of the back buffer. And there's no way to query the format of the back buffer until GLES 3.1. So there was not a solution for us. So we did a trial and error. So we tried to copy the image as a RGB and then fall back to the opaque RGB copy. And that solved the EGLFS issue once. It got broke afterward again. For the delay problem, we just found that the assumption on what Qt 6 was doing was not right. We've changed a couple of signals, so we do things at different moment, and it started working. When you actually steal from the back buffer, you need to be timed with the application's rendering. So it's not the most robust approach, so we fixed it. There's a big unfortunate aspect is that it does not work on big GL, does not work on desktop GL, because when you're on desktop, Qt 6 does extra caching, which breaks it again. But it breaks it in a way that we're back to 3 frame where we were at about 5 frame delays before. So still an improvement. Yeah, and then I had to refactor a lot of stuff in V4L code in GStreamer in order to fit the DRM negotiation. And yeah, everything else, I got loads of backports I did during this projects for everyone to use. So 1.4 stable V4L2 support has more stuff, more bug fixes in. So I took the opportunity to just go ahead, find fixes that are useful for me and others, and merge it as a pool. I implemented the DMA DRM. Hopefully at the Hackfest, I'm going to be able to make the merge request for this one. And then goes the Linux development. So I went in the scaler, I added the mapping for RGBA, and I implemented the color space, the support to apply color space. These are also coming soon. There's little things that I had feedback upstream that needs to be done differently. I'll get to that. And at the end of the day, I had one remaining patches, ugly patches, which it's an embedded project. It's acceptable. It's just one, but I don't really like it. It's because you remember this EGLFS thing about opaque buffers. Well, as soon as you fix the EGL image, you need actually the EGL image backend format to be opaque too. So the hack is basically to simulate, to say that, well, it's RGBA, but we just tell GL that this is actually RGBX. This is a hack. The proper fix would be for QML6 source to negotiate RGBX instead of A, and then it's a Pandora box because you need to plumb RGBX support within the GStreamer GL stack. So yeah, something I'll probably look into, but we might also just redesign the QML6 source. 5 minutes? Perfect. And there we go. We get to the result. And for that, I thought that what is best to demo a Qt 6 application? Well, I made a GTK4 application to help me show that. So on your left, you got the HDMI output from my board over here. If you want to see it, you can come by afterward. So I got an IMX6 board running off a battery with an HDMI capture. This is on the left. On the right, I use UDP streaming simply for testing. I didn't want to do the free RDP thing myself. It was not useful. So it's an RTP viewer. So the demo has before and after. So this is going to be the state before, but after I fixed all the bugs. So it's without the zero copy. The graph on the top from the Gallium hub is your frame rate. And the second one is the CPU usage. And finally, on the right, that's the receiver, and at the bottom, that's FPS displacing, giving us the receiving frame rate. So we start from about, 17 frame On the left, very unstable frame rate that's highly typical to an embedded board that has maxed out its bandwidth. So everything becomes jittery. CPU usage about 20%, I think. I don't see it from here. And yeah, only 6 frame made it through the streaming. And then if we look at the pipeline after, now we actually have 33 frames per second, which is what the application is expected to do. Oh, I forgot to show you something. We'll see. And yeah, finally, we actually saved about a couple of percent on the CPU, but that was not a big deal. The CPU is pretty free. And finally, we have all the frames coming in on the other side. Another aspect, let me go back to the before. Hopefully that's gonna work. Yeah. So you can see that the reaction time, because it's a remote UI, and the reaction time was pretty slow actually with the maxed out thing, because I mean there's only 6 frames per second, so you got a sixth of a second in reactivity, like reaction. And then right after, we end up with something that was fairly decent. So everyone was happy, great success. Yeah. I want to thank, of course, my customer, which didn't want to be named, and AMD for the zero copy work that they made, that Jacobs made for them for the MA35D accelerator cards. So that was quite great. So thanks everyone. And I don't know how many time we have for question. 2 minutes? 2 minutes. So that's probably 3 questions, 4 questions. So.
You mentioned that usage of the GL elements to the flipping and color conversion were problematic because of bandwidth problems. Of course, it would be entirely feasible to have a single pass for the GPU to do the flipping and all those operations. Would there be a way to do that? I mean, maybe not with the element JStreamer today, but looking forward to the future to kind of combine shaders in one pass?
So I'll give a little secret about us, embedded engineer, making project with the libgcgl. libgcgl is awesome to move data from one domain to another. So from your CPU to the GL space, from DMA-BUF to GL space, or maybe to translate CUDA to GL and everything. It's awesome. When it comes times to processing, the filter model is just known to be trivial and inefficient. Every single element does a render pass. So when we do serious projects around this and we have a use case, we actually do a combined implementation. And that could have been my plan B in this project if the output to NV12 was an option. I would just simply say, okay, well, I'm going to combine GL flip and the conversion together and save basically on memory bandwidth. So that's the right approach. Make a GL software, that, especially with OpenGL, where you don't have that many options to combine programs. Usually the easiest way to combine program is to concatenate string before compilation of your program. No, that's serious. That's what we do for real. It's not like a joke. We actually do that in many places. So yes, you prepare yourself. If you need to do a complex payload like live video mixing with multiple output and stuff, you're gonna write a GL program that is wrapped into a GL elements that implement your use case in a fully efficient way. Otherwise, you have to use a bigger GPU and you have to waste some of your resources.